and welcome to Maya as Editor, the game development approach of Santa Monica Studio. I'm Stephen McCauley, I'm a technical director here at SMS, and our co-speaker today is Matt Patinio, our lead rendering programmer. Now, both Matt and I are fairly recent to the studio that started back in 1999, so in talking about the engine today and the choices made, we weren't there at the time. However, we both have worked at studios that used Maya as an editor before, so we do know a little about the choices that people make, and we can observe now how our use of Maya at SMS has affected the studio culture. So although we can't answer to the origins of many of these things, hopefully we can still give you a good explanation of how SMS works today. As I mentioned, our studio goes back to 1999. And although we're primarily known for the God of War franchise, we actually started off with a game called Connectica, which, to be honest, I didn't even know until I started writing this talk. We're most recently known for the God of War reboot in 2018, and its follow-up, our most recent release, God of War Ragnarok in 2022. So yes, we use Maya as an editor. Why would we do that? Well, actually there's many good reasons. Content creators are really familiar with the tool. They know how to use Maya to make art. Thus, it's a very, very, very easy ramp-up curve. There's also no need to write your own editor, which is a great reason when you're starting a studio. It's also a very extendable application. It's very easy to add your own UI and tooling. And a reason why I think historically many first or second party studios have used Maya as an editor is because there's no need to maintain a PC version of the game. After all, you're just shipping a console version. Why make a PC version at the same time just for editing? So for us, all game content is assembled in Maya. Meshes, animations, game objects like collision or trigger volumes or scripts. You might ask us, well, how do you live edit? Well, we do always run the game on console, but Maya has a livening connection to the game, and this provides real-time updates as you edit in Maya. Matt is going to talk a lot more about this later in the presentation. Now, how does this affect our game development? Well, our engine is built around Maya concepts and hierarchy, as we'll explain. Content creators were given a lot of control. What you can do in Maya, you can do in game, with obviously some exceptions, but often it feels that way. And it means we tend to have more focus on build time systems and tools, as opposed to runtime systems and bespoke technical features. For example, we'll go into this a bit more later, we have no terrain system. Everything is mesh. So let's begin by talking about some base engine concepts that will help ground us for the rest of the presentation. So our game is split into WADs. These are the fundamental building blocks of the game that are built offline and then they're loaded, unloaded, or streamed by the game. Each WAD has its own specified memory budget. With very, very explicit memory management. So just for an example, a section of a level is a WAD, but also Kratos is a WAD, or Atreus is a WAD. All characters and NPCs are. Each WAD has a definition file, a .waddef, which states which Maya binary files to load and build, and also you put the memory budget there too. Now these root Maya files are kind of parent files that reference, say, a viz file for visual and art content, a col file for collision data, a nav file for nav mesh data, and more besides. And of course, once you start opening up these Maya files, you'll then find these are long hierarchies of ref nodes. For example, let's see this tree outside of Kratos' house in Midgard. We have ref nodes for each of the tree in this level. Then each tree has multiple ref nodes for trunk and for branches. I've used the word ref node a lot, and what that means is where a ref Maya file is referenced into another. Now, our game is fundamentally built from long hierarchies of ref nodes. Each ref node is built separately and stitched together using a tool called linkwad. Linkwad collects all built Maya files that make up a WAD and links them together. We obviously do customize Maya a lot. We actually have 100 custom Maya plugin nodes, or over 100. These could be entities, sounds, lights, wind, camera targets. And we use attributes on the node to store their data. Maya's native attribute editor provides a user interface, which is very convenient. Nodes can have many custom behaviors as well as custom visualization. So for example, let's look at our light plugin. You can see this is a spotlight. We have visualization for the cone angle and the attributes there too. Now, how do we get this into game, this data? Well, we use something called a data compiler, a very original name, of course. And this is a custom data definition language to describe node properties. The data compiler generates C++ code for setting up attributes in the Maya plugin node, or the runtime data class used by the game. And there is a simplified setup here for nodes that just need to store data and do nothing fancy. So now that we have that grounding about how the game is built in Maya, let's delve deeper into our engine architecture and how it's influenced by Maya scene hierarchy. So we use an equivalent of an entity component system, but with slightly different terminology. Game objects are entities. These game objects have hierarchies. For example, they have a parent and children. Clients are equivalent of components. And we have servers that manage a list of clients. Now, this is good data-oriented design. For example, all light clients are updated by the same server in one big list. And this architecture actually goes all the way back to 1999 and the studio's founding. Now, some programmers on our team are probably screaming at me right now saying it's much more complicated than this, which is true. There are cases where servers are entities and clients are also entities. But this whole system is outside the scope of this talk. And for our intents and purposes, thinking of game objects as entities and clients as components will get you pretty far. So let's look at some example clients that are relevant to rendering, with lights, static meshes, models, also FX blenders, regions of the world that might include cube maps or a lighting environment or color correction. Let's look at the layout of a simple Maya scene, and we're going to use one of our visual tests, triggervol multi-refnode.mb. It's just a quick example. This has two ref nodes that both reference the same Maya file, triggervolumetest_source.mb. Also contains a camera and a lighting environment. Let's open the trigger volume test ref node. You can see inside we have an embedded ref node. This is where data is sort of embedded right into the scene. This is an instance ref node. We have lights, meshes, and transforms. Now, what creates a new game object out of these and what becomes a client? There are some simple rules for this. Root transforms in the Maya scene become a new game object, as do instance ref node transforms. In other words, the parent transform of the actual ref node. Also transforms with the new game object Maya attribute set, if you want to be explicit. So let's look at an example. Cube, this is a mesh in the root of the trigger volume ref node. This creates a new game object called GoCube, and a static mesh client attached to that game object. This is trigger point light shape 2 in the root of the trigger volume test ref node Maya binary, so it creates a new game object, and also creates a light client attached to that game object. However, here, this light does not create a new game object because it's under the group 1 transform, which is not, so it's not in the root of the ref node. It does, though, create a new game object for group 1, Go group 1, and it creates a light client attached to that game object. You can also flag objects to be explicit game objects. For example, if you need to refer to them in script and have them interactable in some way. Another such flag is keep joined, and this means the transform of this part of the object will not be baked. Now, that's a possibility to animate. Let's look at another example here, cube 2. This is instance ref node transform. This creates a new game object, Go cube 2. But let's look at cube. Now remember, instance ref nodes are built separately, so we don't know about the surroundings from building. So cube is in the root of the cube 2 ref node scene, so we create a new game object for cube. So when cube 2 is instance trigger volume test, we have this new ref node hierarchy. It looks something like this. We might have a root game object, we then have the trigger volume test game object, the cube 2 game object, and then the cube. Now, recall that our artists build really long hierarchies of ref nodes. This means we create a lot of game objects. For example, in this scene, we have all these game objects where none of these are animated or scripted. They could all really be just one mesh. So in God of War 2018, we introduced a static mesh optimization. This is performed in linkwad, where, if you recall, all Maya files that constitute a WAD are stitched together. This pulls all suitable mesh instances out of the hierarchy, gathers them into new level objects, transforms and other inherited projects are baked in, and the original game objects are stripped out of the WADs. If we look at an example in God of War 2018, we had 1.8 million game objects, but only 185,000 of those were directly animated. Some of those were transform animation and some of those visibility animation. We only need to keep the directly animated game objects in principle, but just recall the static mesh optimization will apply only to meshes. So some non-directly animated game objects of particles, collision, etc. will remain. However, when we did apply this optimization, we did get nearly a 90% reduction in the number of game objects. This is really pretty phenomenal and was a huge win for the project. However, hold on a second. We've just flattened and merged part of our ref node hierarchy here, but what if we need it? Let's think about LiveLink, our tool that sends live updates from Maya to the game. If I move Cube 2, how do I tell the game to update its transform? After all, we've merged and flattened it. Well, it turns out we keep the hierarchy as LiveLink only, stored as debug data. And LiveLink is a really big part of our engine, so we need to talk some more about it. So I'm going to hand over to Matt now to go into more detail.
Hi everyone, my name is Matt Patinio and I'm the lead rendering programmer at Sony Santa Monica Studio. For this next section I'm going to talk a bit about how we do live editing at SMS as part of our core workflows, and also talk a bit about the underlying technology that we use for implementing live editing. LiveLink is the name that we use internally at SMS to refer to our framework for passing data between our various PC-based tools as well as the game running on the console. The main goal of this framework is really to allow tools to live edit aspects of the game while it's running on the console, which our tools generally do by sending messages and data across the network. The ability to live edit is extremely important for our development, as we don't have a version of the game or engine that runs on the PC, which means the game must be running on the console in order to actually see the final rendering, animation, or gameplay results. While we do have some limited ability to preview assets directly on the PC, which I'll talk about a bit later, in general we rely very heavily on LiveLink workflows to get feedback on changes as we're making them. Before I go over the use cases for LiveLink, I wanted to give a brief overview of how LiveLink works under the hood. To start, we have this diagram here that kind of shows the general connection and data flow for LiveLink. So on the left side, we have a group of LiveLink clients, which are each an application that can make a connection to the central services so that they can ultimately send messages to LiveLink servers. The clients are typically custom in-house tools that run on the PC, but they can also include third-party tools such as Maya, where we integrate LiveLink via plugin. The middle shows our persistent services, which we refer to as SMS services internally. These services are always running in the background on the developer's host PC. The Redis transport service is the important one here, but we also have some other services available for other use cases. We also have a service that provides debugging and logging for all LiveLink traffic, which can be useful for kind of inspecting what a tool is doing or diagnosing a problem when it comes up. Finally, we have our LiveLink servers on the right, which are the apps that receive LiveLink messages and can ultimately respond to them. The main server is the game, which is the recipient of the majority of our LiveLink messages. But there's other tools such as a material editor or material baking system that can also act as servers to allow the game to send its own messages to them. So under the hood, LiveLink works with a set of wrapper functions that's known internally as SM API. These APIs basically form a broad API that clients can use to communicate with the game and send it messages and data, with the calling code basically being regular C++ or C# that can call these functions. Each API call has a unique message that gets sent, which can include an arbitrary payload. We use protocol buffers for these payloads. So basically we have the protobuf DDL language we write, and then our our code compilation system automatically generates the protocol buffer structures and bindings. And this includes automatic serialization that gets handled for us, which is useful so that we can transmit these message payloads over the network. And the way that the communication happens is that the LiveLink system opens a network connection to the Redis server that's running locally on the host PC, and then uses Redis pub subchannels to publish the messages to a particular channel. These channels roughly map to a particular LiveLink server, which allows those servers to pull the messages intended for it from Redis. Since it's happening over the network, this means the servers can be running on a console or on a remote PC, or it could be a process on the developer's host PC. Messages also allow replying with results, so you can do RPC style calls where you get the reply instantly and don't have to do an extra step. So now let's look at some of the clients that make use of LiveLink. To start, I have a video here which shows Maya connecting to the game. So on the left here you can see the Maya viewport with a simple scene open, and then on the right is this scene running in the game on the console. So you can see as I move the camera or interact with other nodes in the scenes, the changes are propagated immediately to the running game, so you can see the feedback in real time. I also have the ability to do limited duplication of meshes and other certain nodes, which you can see I did there at the end of the video. And in practice, there's actually all kinds of things we do over LiveLink, which I'll cover some of them later, but the full list is too much to talk about here. So another LiveLink client is our Visual Script Editor. This is a newer tool and system that was added for God of War Ragnarok to replace previous Lua-based scripting solutions. The script editor has debugging functionality built into it that works by connecting to the game over LiveLink and then communicating state back and forth. So you can, for example, you can set breakpoints in the editor and know when those are notified, or use other debugging facilities to inspect the script's running state. You can also make edits to the script and then automatically propagate those changes back to the game and see the results immediately without having to restart. If you're curious for more information on our visual scripting system, you can check out our presentation from GDC 2023, in which there will be a link in the slide notes. And for an example of a more unusual client, we also have our automatic performance capture and telemetry framework. This system uses LiveLink to gather performance stats from the game itself as it's being run by developers, which can then be visualized and queried through a web interface. The data can be used to easily see which areas are over budget and how they're trending over time. The tools also support generating heat maps, which can be really useful for locating problematic content in the game. The virtual file system is a core piece of engine technology that's kind of existed since the studio's earliest games. And while it can be used more, it used to be used more broadly for core game data. These days, it's mostly used for development-only tweak variables. And then the VFS tool that's pictured here is an internal tool that runs on the host machine and exposes a simple GUI for interacting with these VFS tweaks. So it's similar to an IMGUI debug menu, but obviously it's running on the host PC instead of in the game itself. So this tool uses LiveLink to query the overall VFS directory structure and which variables are inside of them. It also gets the type of the tweak and its current value. And then obviously it lets you change the value of the tweak, and that'll propagate that back to the game. And then it also will show you as a convenience which tweaks have been modified from their original state, so you can see what you've currently modified in the game. And then we have Mesa, our internal material editor, which utilizes LiveLink extensively to allow live editing and preview of materials in the game. So this includes modifying simple float or color properties, as well as assigning new textures. I'll be talking a bit more about Mesa in the next section. So swinging back to Maya a bit, we can talk about how live editing is implemented inside of Maya. So Maya is probably our most important live link client since it's the main interface for editing the game world. And since Maya is a closed source third-party tool, we utilize Maya's plugin architecture to extend it with our live link functionality. This plugin works by registering node add and removal callbacks using the Maya C++ API, which allow the plugin internally keep track of every node in the scene without having to constantly poll and traverse the DAG or anything like that. So once a plugin's aware of a node, it can then register a callback to have Maya notify it whenever an attribute has been either modified, added, removed, or renamed. So these attributes on Maya nodes really encompass all sorts of things. That includes like built-in Maya properties like a translation, rotation, and scale. But it also includes custom attributes that our plugins register to represent data that is really only meaningful to our engine. And based on what attribute changed, a plugin can then extract the relevant information from the node and attribute itself, package it up in a message, and then send it over the game over LiveLink. So at minimum, this typically includes the node GUID as well as the attribute name and value. Then on the game side, once it receives this attribute change message, it can look up the game object and the game client from the GUID and then call a virtual method on it so it can handle that attribute change message. So some clients have special case handling where they might need to update additional data structures in response to an attribute changing, but in many cases we have a generic path for data compiler nodes that simply copies the new attribute value to a location in memory. So it's nice for these DC nodes. We have a simple path that doesn't really require any programmer intervention to make that work. Now our LiveLink plugin does more than just track and replicate node attributes. The full list is a bit too large for this presentation, but I can provide a few other examples. So we have another important one that we have in Maya is we can sync with Maya's animation timeline, and have it sync up with the game. So this way you can control the animation state directly from Maya or scrub it back and forth, and you'll see that reflected in the game itself, which is really useful. Then you can also, if you make edits to certain animation curves and other data, the plugin can track that as well and notify the game so those changes can be replicated on the fly. And then finally, we have a bidirectional camera link, which you saw in that video I showed before, where basically you can have two modes there. One where the game is synced to Maya's camera, so you can use Maya's camera to control what you see in the game. And then you can also go the other way, where the Maya camera is synced to the in-game camera, so that can be useful to if you want to get synced up to where the current game player is in the game, especially if you're trying to find where they are in like the larger game world. It automatically move the camera there for you. So next, I would like to talk a bit about Mesa, which is our in-house material editor. Mesa is actually our second generation material editor. It was written during the development of God of War Ragnarok to replace the older legacy material editor that had been used for previous titles. Currently, almost all materials are created and edited with Mesa, with the exception of a few legacy use cases that have not been replaced yet. So from a high level, the one thing that's kind of important to note about Mesa is that it exposes a fixed set of controls and parameters for the material, and that's all directly tied to handwritten Uber shaders. So in other words, it doesn't have a flexible layout or a sort of like shader graph interface where tech artists can kind of define their own interface and logic and behavior. In our case, it's just a fixed set of features and parameters and controls that are tied directly to the handwritten code that ultimately feed into our core BRDFs. So the underlying Mesa material model here uses a shading model that is in fact a principled shading model, similar to what you might see in OpenPBR. What this means is that the shading model has several features that correspond to different BXDF terms for diffuse and specular, which can be enabled and controlled independently with well-defined interactions. So at a core level, we have Disney diffuse and isotropic GGX specular, which serves as a baseline used by most materials, but we also have optional features such as anisotropic GGX, subsurface scattering, specular transmission, retroreflection, procedural sparkles and glints, and also iridescence or thin film effects. We also have a hair BXDF that's based on the Marshner model, which for the most part is mutually exclusive with these other shading features. So internally, Mesa materials are built around a layer stack. This stack is similar to what you would see in Photoshop or Substance Painter, where the stack defines an implied order of how the layers are blended together. The result of blending these layers is ultimately the final surface and shading parameters that feed into our principled shading model. So really this is a what you'd call horizontal layering, since we're really just doing parameter blending here. We don't support any kind of arbitrary vertical layering, which would require evaluating multiple interactions as light scatters into and out of physical layers. In many cases, a single material is really effectively a metamaterial, which is formed by combining many individual submaterials together through layers. For example, stone might be one layer, with moss being a secondary layer blended on top. So to facilitate this, we support layer referencing, which allows our artists to create a library of base materials, and each of these base materials can then be used as individual layers and pulled into other materials. So this avoids having to replicate these, base material properties for each potential layer combination that we have in the game. And each layer exposes a uniform set of what we call channels. Each channel is typically a combination of a texture map with a set of parameters that combine with that texture. The channels then map to some major component of our shading model. For example, we have base color, normal, emissive, gloss, AO, scattering distance, and iridescence, all as exposed as separate channels. For multi-layer materials, the secondary layers are set up such that each channel must opt in to participating in the blend. So this means you could have some set of channels on the base layer and then only a smaller set of channels on the secondary layers, and so that way you only override those channels rather than affecting all of them. And each layer also has a set of UV transform properties that affect all channels in the layer. So this includes relatively simple operations like scale, rotation, or scroll, but we also support more complex operations such as flow maps and parallax mapping. Then in Mesa, each layer can either be live or flattened. So for live layers, we fully evaluate the layer at runtime in the pixel shader and also blend the results together in that same shader. For flattened layers, we instead we do evaluate that layer and blending offline in texture space. So this produces a set of pre-blended textures. So this way you save the cost of having to do that evaluation and blending in the shader and instead do it offline. This happens automatically during a step in our content build pipeline based on how each material asset is configured. And then ultimately, it really uses the same logic as our live layer blending so that the results are kind of consistent and expected. So the main advantage of doing it this way is that it's fully built into our material editor as a first-class citizen, and it's also part of our build pipeline and avoids the need to have to go out to an external tool such as Substance Designer to produce textures. Although I will point out that we do, of course, use Substance Designer quite a bit internally. But this also represents a pretty significant trade-off for us on the rendering team, since flattening adds pretty considerable complexity and maintenance costs for us. And then another thing I just wanted to point out quickly is that since flattening is first class and so easy to use, it hasn't sometimes been overused to a certain point, where in some cases flattening could be used to produce a unique set of textures, where say a simple tint in the shader would have sufficed and saved both memory and disk footprint. Then in terms of how our materials map to actual compiled shaders, basically each material in the build pipeline will generate a block of shader code that corresponds to exact options and parameters that were configured in the material asset. The bulk of this shader code takes the form of structs that contain hard-coded parameter values for things like tint colors and flags. The remainder is mostly comprised of code to sample the assigned textures for a particular channel. And this part of the code is also responsible for applying any of the requested UV transformations before sampling the texture. So this generated shader code then ends up being included by our handwritten Uber shaders that form the overall structure of the pixel shaders. We have a generic set of functions and utilities that can use the generated code to calculate the alpha value first, then evaluate the layer channels, and then finally blend the channels based on the alpha value. In practice, we actually have a set of different handwritten Uber shaders that are used for different purposes. For example, we have one for rendering opaques to a G buffer, and then we have a different one for rendering transparents with forward lighting. Ultimately, our build pipeline ends up generating, compiling n sets of shaders for each material, where each set has a vertex shader and a pixel shader at minimum. Most of these sets are tied to a particular variant that might be requested by the mesh using the material, such as skinning versus non-skinning. However, in some cases, we also have special rendering paths that activate for certain material features, and these result in multiple passes at runtime with different shaders, and this will result in the build pipeline generating these additional shader sets and compiling them. Mesa does also have a real-time preview built into it that's rendered on the host PC. This preview image is generated using a set of bespoke DirectX 11 shaders, which end up actually including some of the game's actual shader code, mostly to perform the same BRDF evaluation that we would apply in the game. But this is ultimately done in a very simplified forward lighting environment, since the Mesa codebase is much simpler and separate and doesn't have nearly any of the same rendering features that the game has. So instead, Mesa just uses a very simple pre-convolved HDR lighting probe and an analytical directional light, and that's it. For many shading features, this is enough to get a good idea of what it's going to look like. You can see your normal maps and things like that. But some of the more advanced ones, like subsurface scattering, just aren't replicated here because Mesa lacks the rendering passes that we normally use to generate that effect. Then another thing I should point out about this approach is that since we're including our some of our game shader code in these DirectX 11 shaders, that means that shared code has to compile under FXC, which has a very limited feature set compared to other more modern compilers. And as a quick aside, I also wanted to briefly cover how our materials are represented in Maya. So for Maya, we have an additional plugin that interacts with Viewport 2.0 to override the shader and textures that are used when drawing a mesh. This lets us plug in our own shaders that Maya will use when it's drawing into the viewport, and then these shaders can approximate the look of the mesh in the actual game. So the way we do this is by having an additional base Uber shader that it also includes a generated material shader code, just like our in-game shaders. However, in this case, the shader is set up to use Maya's mesh and lighting inputs, which it ultimately does to calculate the final rendering using a forward rendering setup. And so what this means is that the shading parameters that the shader generates inside are actually match what the game has very closely. We have the same normals and base color and things like that, but the lighting environment is completely different. Just like the Mesa preview, it's going to have only simple forward lighting, and we're going to be missing all the fancier passes that we do in the game's renderer, so that causes the visuals to diverge quite a bit. And it's also worth pointing out that this is, of course, another place where we, have to compile a subset of our shaders in a DirectX 11 context. So FXC is again limiting what features we can use in that portion of the shader code. So getting back to Mesa, I want to finish off by talking about how LiveLink works to implement live editing within the game. So this workflow is absolutely critical for authoring material, since it's the best way to see how a material actually behaves and responds with the game's full lighting environment and features. So the way it works is that Mesa internally tracks changes to the underlying material document as the user makes them. And then as these changes occur, they're sent off to a thread, which will perform necessary processing to figure out the steps that needed to live link to the game and update it with these detected changes. So when the user first makes a change over live link, usually the first step that happens is Mesa will compile on the fly what we call a half-baked variant of the material shaders, and the game will switch to those once those are compiled. So these are development-only variants of the shaders that replace the hard-coded parameters with constant buffer values, which then basically allows those parameters to be live updated by the game. So Mesa can then, for each parameter that changes in the UI, Mesa can form a live link message and send over the name of the parameter and the value, and then the game can respond by updating the constant buffer. So obviously, some material changes can't be represented with just a simple constant buffer tweak, and so we instead will need to have Mesa recompile the half-baked shader again and then send it back over to the game. So for example, this will usually happen when texture assignments are changed or if a channel is enabled since the texture sampling code is generated, and so we need to regenerate that, then recompile the shader. There's also some features that require a particular preprocessor macro to change, for example, to change what the inputs and outputs are to the vertex shader. In all these cases, Mesa is pretty good at figuring out whether it needs to recompile the shader, and if it does, it will do it on the fly and kick off compilation jobs. And then one side benefit of this system for shaders is that it can serve as kind of a handy live reloading path for when rendering programmers want to iterate on a particular material's shader code. Since our material Uber shader code is shared by many, many materials, you often don't want to recompile all the materials that depend on it, but instead you just want to build one particular material. So this path in Mesa lets you do that by enabling live link and making a change to the Uber shader code and then updating the game with that, and that works nicely. And then finally, Mesa also supports live updating of assigned textures. This includes both adding a new texture to a previously empty slot or changing an already assigned slot to a different texture. Additionally, Mesa will watch for file changes on the actual source image file for a texture and determine if it's been modified by an external tool like Photoshop or Substance Designer. So in all these cases, when Mesa picks up on a texture change, it will kick off our actual normal texture build pipeline, which will load the image file, generate bitmaps, and compress it to the final BC format, things like that. And once that's all done and we have a processed texture, we can package it all up in a live link message and send it over to the game, and then the game can load that new texture data and you'll see the visual results immediately. And now I'd like to hand things back over to Steve McCauley to talk about the influence that these systems have had on our design and studio culture.
Thank you, Matt. Hopefully you've seen how Mesa Material Editor has developed and is influenced by how we build our game in Maya. But now let's talk about some other influences. I'm going to cover our mesh pipeline, our animation system, and also our team culture and structure. Now, as mentioned at the start of the presentation, everything on our game is hand-altered mesh. We have no terrain systems or equivalent. This is really powerful because what artists want to build, they can. It also means we do extensive uses of skirting to help meshes blend together. So let's dig into the pros and cons about not having a terrain system. Well, for one, we're not constrained by a 2D height field. Overhangs aren't really a problem here. Artists, again, can create what they want. However, they do have to do a lot of extra work. They have to manually break up meshes and also make LODs. It also means code-wise, other terrain-specific optimizations are harder to do. For example, you might have a virtual texturing system just for terrain, or procedural material generation across the terrain. For us, these would have to be generic systems across the whole game. This has also actually influenced our studio culture. Since there's no automatic distance terrain, we employ a Vista artist to build vistas for us. It also means when we want to implement a feature like snapping meshes to terrain, for example, conforming the roots of a tree to the terrain, with a height map terrain system, that can just be a runtime shader feature, sampling such a height map. But at SMS, this is a Maya-based tool. Snapping would happen perhaps when you click a button to bake, or automatically when you save a Maya file. I do think this actually helps us longer term overall. So for example, we are currently working on a hierarchical LOD system that works for all meshes, rather than just having something for terrain, having to build a separate system for all meshes on top of that. We're going to build a system that works for everything. Skirting has been a big topic for artists, many companies I've worked at. We've solved it in the past in other ways. For example, you have a terrain system. We've deformed objects to the terrain height or blended terrain albedo into objects that sat on the terrain. It's also been a demand by art direction to ramp up SSAO to solve the skirting problem. And yes, I know that's not the best solution. But here, as everything is just mesh in Maya, we're able to solve this artistically by hand placing mesh everywhere. This, of course, is very art intensive, and we've developed a couple of tech features to help out. Let's look at this example from Midgard. You can see all the meshes highlighted in green here. If we zoom in a bit to look at a tree, you can see this tree mesh without a skirt, and what it looks like with the skirt enabled. Now, the purpose of skirting is to ensure that mesh should fade when they join other meshes. But how about they happen in general, avoiding the need for skirts? For example, you might think a very brute force solution here is to use alpha blending and use a feature often used for particles, soft alpha, where you read the depth buffer and fade out a mesh where it's close to the depth buffer, where an existing mesh is. However, there's an optimized solution for this from Bart Wronski on God of War 2018. We modify the depth of the mesh to fade in a dither pattern. So just for example, if we offset the depth by up to 5 centimeters, well, the mesh will start fading out when it's within 5 centimeters of another mesh, and it's fully faded out when it's 0 centimeters away. We conservatively modify depth, of course, to preserve early Z here. And we fade out this feature, because it's pretty expensive still, up 50 meters from the camera. Here's some code for you to look at in your own time when you read the slides. So we often use depth fade to blend rocks against the terrain, so let's look at a simple example of that. Here is a rock with no depth fade, and this is what happens when we enable a depth fade of 3 centimeters. You can see it gets a lot softer. Let's look at this again. Another tool to help meshes blend together is vertex painting and vertex colors, and we use that a lot to blend between different material layers. As the whole level for us is loaded in Maya at once, we can vertex paint across the whole world. This is called our ref paint tool. And this can really help blend two meshes placed next to each other because we can blend to the same material layer on both meshes. And it feels a little bit like another example of what you can do in Maya, you can do in game. But how does this work for instances? Well, we need a separate data set for the vertex colors for each copy of the instance then. But then what happens if an instance changes? Well, then all vertex paint data is invalidated across the world. So actually what we do is store the vertex colors in a point cloud. If the underlying mesh changes, well then the painted point cloud of course remains the same. This is then projected onto each mesh at build time. And again, we still have a copy of the data for each instance. The downside of this approach does cause some build dependency problems. If an instance changes, we need to rebuild the vertex color data for it in every place that it's used. Let's look at another example of using skirts and also using the ref paint tool. This is Kratos' house in Midgard. You can see the geometry here for the skirt, where Kratos' house joins the terrain in green. Then we enable vertex colors. You can see how the skirt is painted white and the black at the edges to fade out. You can also see how the vertex colors are painted across Kratos' house and also the terrain in front of the house. Another example of something artists can do in Maya that comes into game is animation. We can animate meshes, the transforms of visibility, and also material parameters. One engine I worked with is actually a feature request from the rendering team to have light bulbs swinging rather than something the content team just created. For us at SMS, really they could make the light bulb swing in Maya with a simple animation and it would come into game. There'd be no problems, no feature request at all. So let's look at how they might do this. These are our meshes highlighted in green. Then if you look to the top right, you can see the Z chord of the transform in red, meaning that it's animated. We right-click and open it up. We can see the animation that we've assigned and we can edit it. This is a pretty simple back and forth animation that we're editing in Maya and it comes right into game. As you can see, content creators are really empowered at SMS to build levels. That means they actually really take responsibility for quality and also the performance. They want to make things run and they want to make things look good. Tech then can be viewed a bit more as a tools and support group. On a very occasion, I've seen the attitude from artists of, well, it's my responsibility to make this level look good, so maybe I don't care about your tech features. That's an extreme point of view. Obviously, it's better to work together, but I think it shows the confidence that the content creators can have in the tools that they have to deliver a really great product. This also means that really environment artists own all parts of their level. The set dressing, the modeling, the materials. Really, they are in some way just creating something beautiful in Maya from start to finish. We do, though, separate out level design and environment art. The level design will first author sheet mesh, as we call it, or maybe grey box as you do, and then they hand it to art. There is then, of course, a lot of back and forth here between art and level design over things like metrics, readability, collision, just to make sure the level is very playable. Let's look to the future. Obviously, using Maya as an editor isn't all rosy. There are some problems. We do have plans to overcome them. Build time can be pretty terrible. The performance of Maya itself is an issue. And a really heavy dependency on Maya for everything can become a problem. So, for example, initializing the Maya library takes 5 seconds. And in total, we spend at SMS 160 hours a week to process content through the Maya API. And these figures from a year or two ago, but they haven't changed much. We do have some tools to help us bypass the Maya API. So searching Maya files for dependencies, we use a tool called Maya Ninja, which is a custom Maya parsing tool, which is many times faster. We still need to use the Maya API for building data. Maya is also slow when you try to load a file. When we load a typical game scene, it's actually 5 minutes on initial launch. It's 40 seconds on a subsequent launch. That's because we have a proprietary system to build proxy meshes of the scene for faster loading. But then, of course, once that scene is actually loaded itself, you've then got to load a ref node, and that's another 10 seconds to actually start working on something. So in the fastest scenario here, really, it's like 1 minute for an artist to work on a small part of the level. We've even developed something called the Scene Color tool. This is for animators working on cinematics. It cuts out the relevant portion of the Maya binary scene to the cinematic, and this just significantly improves load times, as animators only need to load exactly what they need for that cinematic. Another problem is everything in our game goes through Maya, and Maya isn't always the best tool for the job. We use Houdini for a lot of procedural development, and there's a rise in junior artists in general who have grown up with using Blender. And for simple level design work, do you really need a really complex program like Maya? For placing something like an audio emitter in the scene, isn't Maya a bit overkill? Finally, it isn't healthy for the studio to be so dependent upon one third-party tool. We're very dependent, of course, on Autodesk for support. We'd like to decouple a little bit. OpenUSD solves many of our problems as a fast API. It's interoperable with many DCCs, and actually OpenUSD editors just already exist out there, such as NVIDIA Omniverse. The OpenUSD API is up to 70 times faster than the Maya API. You just look at this test scene with 1,788 meshes. Compare the Maya in blue and OpenUSD in orange. Orange is much better. And then in opening the Maya scene mentioned earlier, it takes 50 seconds to load the entire level of USD, including all ref nodes. It also means we can delete the proxy system, which I love deleting code. It makes everything a lot simpler. So this is much better for how artists could work. And now, of course, you're going to ask me, are we thinking of developing an editor? And particularly now when we actually are making PC builds of our games. Well, we are for simple level design tasks such as placing audio emitters. We're developing an editor for those, but this is not going to be what you see as what you get. Maintenance for the rendering team here is very high, particularly for DirectX 12. And this also causes a few API issues. We do need DirectX 12, of course, to support all the PlayStation 5 graphical features that we have. But for Maya and the regular viewport, we still need DirectX 11 and Shader Model 5 shaders that the artists use to view. So this is a bit of a catch-22 for us. Longer term, we want to look into Material X for DCC agnostic shader and material support. Now, to summarize, using Maya as an editor has heavily influenced our studio, from engine design and architecture to artist workflows and also our company culture. Maya, though, has also brought many limitations with it, and the future for us is OpenUSD. I would like to thank all these people at SMS for their help with the presentation, and also to all past and current contributors to our engine, and also the React organizers for all their comments and support and organization work on this conference. Thank you, of course, all for listening. And now we'd love to hear your questions.
And thanks to our presenters today for the awesome content. We have tons of questions, so let's see which one we can address live. So first, there are some people who are asking a little bit more generally about Maya itself. We have a question from Tom Everard saying, have new junior members easily gotten onboarded where they were unfamiliar with Maya? Curious as Blender seems to be the reference point for most juniors.
It's a great question. I don't really know. I think a lot of our environment art team, to be honest, has been at the studio for a really long time. We have a really experienced team. So they're like really experts in the tools and they know how to use them really well. And I'm sure they're there to coach any junior artists that join. But I don't think we've had any issues come up, though, as I mentioned later in the presentation, that is exactly something we're thinking about. We want to give that option in the future, just in case it does arise.
Yeah, I'll just like plug in also this one from Paul Zurita, which may be a little bit spicy. Like, what is the perception of the artist working with Maya versus what they see in other engines like Unreal or Unity? And do you know, does it change between environment artists or lighters?
I don't know. I'm not sure I've heard anyone talk to me directly about this on the art side. I don't know, Matt, if you have.
Not really. I get the impression it's more the design side where we have more, comparison, and either unfavorable comparisons to Unity and Unreal, whereas the art side probably less so. But yeah, I haven't myself also heard too much from that.
But generally, I think they're a fan of our engine just because, again, like they can build things in Maya and it comes into game and it looks great. So for them, the workflow can be pretty decent.
Yeah, I mean, like usually, I guess this question comes a lot because, the editor is always greener on the other side of the fence. But kind of like related to the data pipeline, we have lots of questions there. So from Malek Ben-Gugam, we have a question like, assets produced in Maya are rarely production ready. Do you have a pipeline in Maya to cook baked data when using Maya as an editor?
I mean, it goes directly. So again, the data authored in Maya is what is used in game. So there is like a conversion step here, just in terms of, we have an internal format called X3D, and the build pipeline will convert my binary to X3D, and that's what kind of gets baked into the final, WAD build. So, everything is like built into a kind of big condensed WAD file. But generally, yeah, the art they're authoring gets directly into the game.
Okay, so this sidesteps very nicely into this next question from Rodney Huff. If you change a runtime data format and need to reprocess data, do you use Maya headless or Maya libs to access the source data? Or do you export an intermediate format? And if the latter, how do you make sure the source in Maya and the intermediate representation stay in sync?
I'd say it's the same as like most other engines, right? And if I was to change the format of like an X3D file, add like I wanted an extra like flag from Maya to come into the game, then yeah, it would require a rebuild, which is obviously painful and takes quite a bit of time for rebuild content, but it's just sort of the way it is. And to us, it's not too different than other engines I've worked with where you change something like that at the kind of core base file format level and you have to rebuild.
Interesting. Okay. So from Karim Lustin, sorry, I'm messing up the names for sure. I'm guessing my updates are a very big deal. How do you deal with that? Like, do you have some kind of testing to make sure that the next version will still work?
Yeah, so the last time we did a Maya update was actually soon after God of War Ragnarok shipped. It was one of the first things we did, because obviously that was a great time to do an upgrade once you've shipped the game. So we upgraded to 2023. That was actually pretty painful. The reason for that actually, I think, was because we had to change from Python 2 to Python 3 with that. So we have a lot of Python scripts. So it wasn't necessarily the Maya thing itself at that stage. It was really the Python that really got us. And I think we're kind of thinking about maybe doing a Maya 2025 upgrade. And we think that might be easier because the Python stuff isn't going to be as difficult. But we had a lot of like extensive QA testing for a number of weeks on that.
Okay. I think I'll do a couple more questions, like kind of related to the data formats, and then maybe we can switch to the material side of stuff. So we have one from Brad Bloss from Frostbite. The question is there any sort of game bake or import to create packages for ship? How does that interact with the Maya build?
So again, I think it's like everything is like built onto like WODs. So once you've kind of got the WOD, you've got the kind of build. There is like, I think, separate things we do to get like a final, like I think it was a gold, package, which is usually related to textures and packaging the textures in terms of like texture streaming data, like pulling out the top MIPS of all the textures and putting that into a separate package for streaming. But that's like that's so most of the time you don't need to do that because you're running like release. But if you want to test like, final gold version, you have to do that extra step.
Okay, let's kind of like migrate towards the material side. Karim, Lucian asks, what does shader iteration look like when changing materials, but also tech stuff, which here I guess means shader code?
Yeah, sure. I'll take this one. So it's the way it normally works is, yeah, so we have for our Uber shader, as I mentioned, there's a shared set of shader code that's handwritten. And so if you touch that and then you build WODs, you will end up needing to recompile shaders for all the materials that are referenced by whatever WODs you're building. So this could potentially be a lot or a smaller set, depending on whether it's like live content or, your kind of test bed levels. And I did mention in the talk, there is like a way through Mesa you can sort of like use the live editing workflow to just iterate on one particular material, make changes. So that's pretty nice for isolating it and keeping it fast. For our non-material shaders, we do also have like, ways to kind of live edit them where the text changes to them and it'll update in the game. So you can do that too to quickly iterate before you do, once again, build your WODs and do the final build. That'll do the final compile and package it all up in WODs and things like that.
All right. Jamie Hayes asks, do you have any examples of data that can be live edited due to having a largely different data structure game side due to data build processing?
I'm trying to think of any other. Okay, I'll admit the live link code often isn't pretty. Like it's a lot of actually sometimes duplicated code, like in the runtime to sort of like convert from this like format, like basically from like I guess like what the live igniter send across into like the actual game format, which has obviously gone through the build process. So I remember one example is we might have had like, I think around God of War Ragnarok, as I was playing around with flags for modern meshes, things like, does this mesh cast a shadow or not? Or does it cast reflection or GI or things along those lines? And then basically during the bake process, we're sort of obviously combining Maya meshes together, those flags get baked down, and I had to replicate sort of similar code in like the runtime for when you receive live link data to do that kind of baking. And when I didn't, there was like a problem because artists were clicking flags and it wasn't updating in real time. So there is a lot of sadly manual setup for some of these things.
Cool. Well, I have to ask this one because we were chatting about it in the back room. So from Martin Cajon, what is the advantage of having shaders with baked-in parameters as opposed to using parameterization via a const buffer that you use for live editing? This has to lead to an enormous combinatorial explosion of shader variants in the runtime.
Yeah, so yes, that is a very good question. So yeah, we've had this kind of setup for a long time of sort of baking in the parameters into the shaders. There are pros and cons. In general, it is I would say it's not where we want to end up, and we are looking into ways to reduce our number of shaders and use more, shared shaders between materials and constant buffers, things like that. What has been nice, and the reason it's kind of been this way for so long, is by kind of generating a shader for each material, you don't necessarily have to think about like how your features combine in a certain way of like whether it makes sense in terms of like, oh, if I have these features enabled, like, you know, do I need to pull these into certain permutations? You can kind of just have this huge set to pull from that's gigantic, and then they just sort of get turned on, and you know you're getting what, based on whatever features the artists are using, you're getting sort of the most optimal shader for that, in that it's now all been inlined into the compiler. It can make assumptions based on that. If they set a slider to 0 somewhere, it's going to optimize through. But obviously you pay a very, very heavy cost for that in terms of the number of shaders we have to compile. There's also downstream effects from that as well, in terms of having the number of shaders loaded and how that affects your batching and things like that too. So you know, we have plans to try and move away from this. I don't think anything we can talk about right now, but it is not something we're particularly happy with.
Yeah, I think as people like numbers, like I think I said, I think God of War Ragnarok had around 33,000 shaders. I think for other people, like 6,000 to 9,000 unique is kind of more normal.
Okay, that's not even that gigantic. Actually, I wish I could pull Natasha in, but I think like the first time that I heard something of like that was on Destiny. I don't want to be incorrect, but I think they were doing something similar. Let's just do one last question, then we'll go to the closing. So from Adam Sawicki, is testing the game on consoles only? What is the iteration time of changing something in the engine code, compilation, deploy to the console, launch and load?
I think it's not that bad, really. I mean, I think compilation is like no different than, again, I'd say in most other game engines, using a file that can be, you know, pretty relatively quick. Actually, I think, you know, maybe 30 seconds, depending on what you change. I mean, the biggest bottleneck is building data. So like, if you are like changing something that needs to be like, you know, require data rebuild, then perhaps a small test level with a few changes can still probably take, like, maybe the best case, like at least a couple of minutes, the most case more 5. So that can be a bit of an issue. But also we have a separate sort of, you know, build for like, say, system shaders, like post-processing. That again is much quicker to build. So that's maybe like a minute, depending on what shaders you change. Maybe forward plus like deferred lighting shaders take a lot longer than that to rebuild, of course. But generally, it's pretty good. But yeah, running them by the time it launches, I mean, again, it can take a while to load if it's pulling like data across the console mirroring, but sometimes a few minutes.
We do have edit and continue working too.
Yeah, that helps a lot.
But that helps.
Very cool. Well, thank you again. There are a million more questions for you on Discord, but we won't have time to cover them now. And yeah, please hang around for our closing session.
Thanks, everyone.
All right. Hopefully this is correct. So this is the closing for React 2024. And of course, we have to add this slide, just one more thing. First of all, let's just do one last round of applause for all the incredible presenters and their time and their willingness to answer questions openly in the live and being around on Discords and incredible participation. Natasha already did a great introduction on this topic at the beginning of the day, but it's really a gigantic amount of work, and it's harder than it looks like to organize presentations and share with you all in the community, right? Someone was even saying that they found some bugs they needed to fix in order to have the right screenshot in their slides. So even on our side, we thought, you know, this is the second year we do a virtual conference. We had it all lock and loaded. And then in the grand tradition of game development, we just landed hotter than last year. And we know that making games is hard. And I don't want to end the conference, you know, on a bummer and list all the challenges that are in doing this job. But instead, I want to bring our attention to one of the bigger perks, in my opinion, of being in this industry, which is you guys, this incredible sense of community that we have. I'll just take a minute for a short anecdote. My wife and I are both in the entertainment industry. My wife is on the movie side of the business. And we were in Joshua Tree last week. On the flight back to Vancouver, in front of us, there was a writer and director that she has worked with in the past. And I noticed that he was sporting a cap from Game Conference. And so we started chatting. And the moment that he knows that I'm in gaming, he was just like so amazed at our community and this sense of openness and sharing not only of knowledge, but sharing of resources. So we really don't have to take this for granted, because it's very uncommon, I guess, in general, but perhaps even more so in creative industries. I also wanted to share a little bit of inside baseball, some behind the scenes of the excitement from us, seeing you all guys participating and filling our rooms. So thank you again from our whole team for making this year a success. We just provide this space, we provide a venue, but use the people who make it matter, who feel it. And this went beyond our wildest expectation. The participation, the civility, the enthusiasm, our Discords are probably half of the conference. Like if you're not there, you're missing out. And it's just such a heartwarming reminder of the camaraderie in our community. And okay, we ask only a small favor. Now you know what's going to come up. Please fill us a survey. We put it in all the slides, but it's really because we do care and it does matter. And we don't run a town hall event. We want to pack the conference just with content for you. But this is something that it matters to us and it matters to the speakers to receive feedback on their work. Everybody asks about this. There will be recordings. We will work tirelessly to have them out as soon as possible. So monitor both our YouTube channel and our website. And this is all for this year. Thank you and ciao.